Hey guys, today we're going to talk about the movement of matter through ecosystems. We've already covered the movement of energy through ecosystems, and we did that when we talked about ecology and trophic structure in ecosystems. Now we're going to move into the movement of matter, which is the biogeochemical cycles. So the hydrologic cycle, the carbon cycle, nitrogen, phosphorus, and sulfur cycle, and how these elements cycle through the atmosphere, through the soil, and through the water. So some key ideas to keep in mind about all these biogeochemical cycles. AP students tend to get bogged down in the specifics of these biogeochem cycles, but I want you to keep kind of a big picture view of what we're trying to get you to know in terms of how it's going to be tested. The idea that matter cycles through atmospheric, terrestrial, and aquatic systems, and also through the bodies of living organisms. Key idea, big idea, keep that in mind as we talk about these biogeochem cycles. It's also important to understand that some of these cycles have quick phases where the element is cycling in the range of days or weeks. And some of these cycles are slow or have slow components where the element is cycling over the course of years and in some cases millions of years. Some key idea to keep in mind in terms of terminology that I'm going to use when I teach. Matter arises in what we call sources. So when I talk, like for instance, about a carbon source, I mean this is an area where carbon is coming from. Now, I don't mean that it's being made, because matter, of course, is not being created. It's not created or destroyed, but that it's a place where you can find that element in either the atmosphere, the soil, or the water. So matter arises in sources, and it accumulates in what we call sinks. In ecological science, a sink is a place where these elements just kind of build up. And the sources and the sinks flow through biotic and abiotic processes. And you should be familiar with those terms. Biotic means living and abiotic means non-living. The APES exam will test your knowledge of the biogeochem cycles largely through your understanding of how humans alter the natural rhythm of those cycles. Because when you think about the framework of the course, that's really what we're focused on. We are not as focused on the minutia or the little tiny details of each of these cycles, because we're not in a geology class and we're not in an ecology class. We need to take a step back from how they work, and we do need to have an understanding of how they work, but we're going to take that understanding and layer it with how humans alter those natural rhythms. And that's the way that the test is going to approach biogeochem cycles. So we're going to start out with the one that's probably most familiar to you, which is the hydrologic cycle. You probably know this as the water cycle. The hydrologic cycle is the fancy APES way of saying the water cycle. The movement of water through the biosphere is known as the hydrologic cycle. The process is driven overall by evaporation and transpiration. We kind of combine those and we say evapotranspiration. And the source of the driver of that process is, of course, the sun. The heat from the sun causes the evaporation of surface water, and plants also release water through their stomata during photosynthesis, of course, when they're hit by sunlight. And that is the definition, by the way, of transpiration. Transpiration is when plants release water vapor through their stomata during photosynthesis. So we've got evaporation of surface water. Now, it can come from like actual bodies of water, but the soil also has water in it. So evaporation from soil and surface water. And then, of course, transpiration. We kind of combine those and say evapotranspiration. So the water vapor rises up into the atmosphere. It cools and it condenses and it forms clouds. And the clouds eventually drop their water back to the land via the process known as precipitation. When the water falls back onto the land, it can take one of four routes back through the hydrologic cycle. So it can be taken back up by plant roots directly, and it can return to the atmosphere via transpiration. It can evaporate directly from the surface back into the atmosphere. And again, that can be like just the soil, where the rain falls on the soil and some of that is evaporated back up, or it can be from bodies of water. The water can also be absorbed by the soil, and it can percolate down to replenish groundwater. So we're going to be talking a little bit about percolation and infiltration, the movement of water through the soil. And we've already kind of talked about that because we've had our soil unit already. It can also move across the surface of the land as runoff, and that runoff leads the water into a larger body of water where evaporation will return it back to the atmosphere. But again, the drivers here are the sun, which drives evaporation and transpiration. So this is going to come as a surprise to you, but humans screw up the hydrologic cycle. Not a surprise. You already know this. So let's talk about deforestation. Deforestation, obviously, in apes is a bad thing. It reduces evapotranspiration. If the plants are gone, they're not doing photosynthesis and they're not releasing their water vapor, their moisture back into the atmosphere. If they're not releasing their moisture back into the atmosphere, then the clouds aren't forming over that. Forests create their own microclimates through evapotranspiration. And if you remove the forest, then you actually screw up the water cycling in these microclimates because the clouds aren't forming over the forest anymore. Deforestation also screws up the water cycle by increasing surface runoff. When the trees aren't there to buffer the impact of the rain, first off, you get erosion, and we already know that, but we're not talking about erosion here. We're talking about the surface runoff. There's nothing to absorb the water, and so the water just runs right off, and it runs into larger bodies of water. Of course, it usually takes sediment with it, which causes sediment pollution in rivers and streams. But when surface runoff is increased, that means that percolation and infiltration into the soil is decreased, and we get a reduction in groundwater recharge, also along with deforestation. Another way that we increase surface runoff and reduce percolation is by paving surfaces. When we pave surfaces, they're impermeable, and the water can no longer get down into the ground in order to recharge the groundwater. We've actually talked about this before, but I'm going to draw your attention to it again. It's a way that we screw up the hydrologic cycle. And then finally, human diversion. That means that we're taking water from where it would normally or naturally go, and we're putting it either through a series of canals or pipes someplace else. Human diversion or impoundment of water. Impoundment, I'm talking about when we build a dam, when we choke the flow back and we create a lake from what used to be a river or a stream. Human diversion or impoundment of water resources for either domestic or agricultural use also alters the hydrologic cycle. If you're diverting water from where it naturally flows, then the places that would normally get the water are no longer getting the water, and you're diverting it to some place that doesn't normally get water. And of course, impoundment of water, we've talked about kind of some of the negatives of putting a dam on a river. You're changing the whole function of that watershed, so it's altering the hydrologic cycle. Here's a lovely graphic of the hydrologic cycle. I'm just going to follow a few of these around. A lot of this is stuff that you already know. So the sun is up over here, and that's of course the driver of this. So we've got evaporation from surface water here, and then of course we've got condensation. Here's our cloud occurring over here. Clouds, evaporation, there's more evaporation over large bodies of water such as the ocean. This happens to be a picture of the ocean. Prevailing winds, usually when the clouds form over the ocean, they blow back in over the land, and that's usually where they drop their precipitation. So that's what you're seeing right there. Here's our precipitation. Our precipitation is raining back down onto the land, and it can come as ice, it can come as snow, and that's what you're seeing right there, if it's depending on, of course, altitude and latitude. And then as the precipitation runs down, you've got runoff into bodies of water. Surface runoff. Now, surface runoff usually ends up back into a larger body of water, whether that's freshwater or saltwater. It depends on where we are. You can have freshwater storage due to runoff. You can have runoff back into large bodies of water like the ocean. The precipitation also can have groundwater infiltration. And that's what you're seeing there. If it rains onto the ground, we can have groundwater infiltration which leads to groundwater storage, where the ground is actually storing some amount of water. Groundwater storage, it can be long-term or short-term. A lot of times it eventually reaches back into a larger body like the ocean, but that, depending on the ecosystem it's in, it can take a long time or a short time for that groundwater storage to return to a larger body of water. And that is the hydrologic cycle. Okay, so the carbon cycle. Carbon is, when you took biology, we're going to skip those of you that took AP Bio because you probably already know a lot more about these cycles. But when you took regular bio, we obviously introduced you to the water cycle, but we also introduced you to the carbon cycle and the nitrogen cycle. And we're going to go through those again, but we're going to APESify it, which means we're going to go more into detail. So here's the carbon cycle, which you should kind of sort of remember. Carbon is super important to living organisms. It's kind of what we're based on. All biological macromolecules, or what we call in biology biomolecules, those are proteins, carbohydrates, lipids, and nucleic acids, are based on the element carbon. We are organic beings, and in science, organic means it contains carbon. There are 7 major processes that drive the carbon cycle. And I've grouped those processes into, because there's reasons that they go together. Photosynthesis and cellular respiration go together, okay? And we're going to talk about why. Exchange, sedimentation, and burial are our next 3, and they also go together. And then extraction and combustion. So those are our 7 major processes that drive the carbon cycle. Those processes can be categorized further on as fast or slow, meaning that they happen either on the scale fast, like days or weeks, or slow. And in the carbon cycle, we're talking about like years to millions of years. Fast carbon cycling involves processes that happen in living organisms. So your fast cycling is going to occur right here in photosynthesis and cellular respiration. That's how carbon is exchanged in living organisms. Slow carbon cycling is going to involve carbon trapped in rocks, it's trapped in soil, or in petroleum deposits. Now, this part right here, exchange, I usually classify this as fast, and I'll talk about that why in the next slide. Sedimentation and burial, extraction and combustion, all of these are slow. And we'll get to more to this in the next couple of slides. So let's go into photosynthesis and cellular respiration. I did not put the balanced chemical equations for photosynthesis and cellular respiration on here again, because when we did ecology, I already reintroduced those to you. You have to know those. That's a tested chemical equation, and those you should know. If you don't know them, go back and look. They're in a previous PowerPoint. They're in your textbook. You have to know those. I'm not going to review them here, but photosynthesis and cellular respiration are considered quick carbon cycling. There's a word here that I've put in here because you can you might see that on the exam. You certainly see it when people are writing about the carbon cycle, and that is this idea of modern carbon. This is carbon that has recently been removed from the atmosphere. It's cycled quickly through an organism through photosynthesis and cellular respiration, and then it is quickly released back into the atmosphere. I'm going to use a word called, and the word is sequester. Sequester means when an organism or a geologic process grabs onto an element and holds it for a long amount of time. In photosynthesis and cellular respiration, carbon is not sequestered. It's cycled very rapidly. So this carbon is recent or modern carbon that was recently in another being or in the atmosphere. The carbon dioxide released during respiration was removed from the atmosphere via photosynthesis just days prior, and this is why we call it a quick cycle. When producers photosynthesize, they take in carbon dioxide and sequester some of that carbon in their tissues. So you guys know that producers do both photosynthesis and cellular respiration. So some of the carbon that they take in, carbon dioxide that they take in from the atmosphere, they sequester in their tissues for growth and reproduction. They're using some of that carbon to maintain their own bodies. But some of it is released back to the atmosphere when producers do respiration, okay? So, and that's exactly what the next one says. Some carbon is returned to the atmosphere when organisms perform cellular respiration, and carbon's also returned to the atmosphere when organisms die. After death, the sequestered carbon, the carbon that was not cycling through cellular respiration, is broken down by decomposers, and it's returned, some of it's returned to the atmosphere, some of it's returned to the soil, and some of it's returned to the water if there's water around. So that carbon goes back into terrestrial, atmospheric, and aquatic systems. Okay, the next group here is exchange, sedimentation, and burial. So let's talk about exchange first. Exchange is what I would consider quick cycling, and here's why. It is carbon dioxide that is released from the ocean in various processes, and that can include cellular respiration and decay, which are generally fairly quick processes. That carbon dioxide is entering the atmosphere, and that carbon dioxide in the atmosphere is dissolving in the ocean to create carbonic acid and calcium carbonate. This is a continual process. It never stops. So that's why it's considered exchange. So carbon dioxide is released from the ocean into the atmosphere, and carbon dioxide is being dissolved into the ocean, creating carbonic acid and calcium carbonate. And it's an ongoing process, and it's a relatively quick cycle. And I'm going to show this to you when we look at the diagram. Sedimentation, however, is considered a slow part of the carbon cycle. Calcium carbonate can precipitate out of seawater and form limestone through sedimentation and burial. Calcium carbonate, by the way, is the calcium compound that forms the shells of marine organisms. Rock formation is slow. So we've got calcium carbonate. It precipitates out of seawater, and it forms limestone over the course of many, many years through sedimentation and burial. Rock formation is very slow, but over millions of years, sedimentation and burial of precipitated calcium carbonate has produced the largest carbon sink in the slow part of the carbon cycle. Listen to my words. We're talking about limestone. This is a test question alert. This has been asked before. What is the largest carbon sink in the carbon cycle? And I'm going to classify that as the slow part of the carbon cycle. The answer is limestone. Because although rock formation is slow, over millions of years, this calcium carbonate has produced an enormous amount of limestone, and it is the largest carbon sink on the planet. Burial is also considered slow cycling. Dead organic matter is buried, and it's mixed with ocean sediments over time. The buried material eventually fossilizes, and over the course of more millions of years can become fossil fuels. Obviously, the creation of fossil fuels is a long-term process. The amount of carbon that's removed from food webs due to burial is about the same amount of carbon that's returned to the atmosphere due to the weathering of limestone and by volcanic eruptions. So the slow part, sedimentation and burial, that stuff is basically in equilibrium. Now the modern and the quick cycle, that's not so much an equilibrium, and we're going to talk about that when we talk about the ways that humans screw up the carbon cycle. So our final group of processes that drive the carbon cycle is extraction and combustion. These are relatively new things that they began during the Industrial Revolution. So extraction is the extraction of fossil fuels. Coal, oil, and natural gas are fossil fuels, and they're formed from the buried remains of organic material. That means that they contain carbon. Extraction is largely carbon neutral, and by carbon neutral, I mean that it does not add or subtract carbon to the atmosphere. But combustion, the burning of fossil fuels, is carbon positive. Remember, in science, I don't necessarily mean that positive is good. It just means it's adding to a process, and that's exactly what I'm meaning by the word positive here. Combustion is often not positive, but it means it's adding carbon to the atmosphere. Combustion releases this previously sequestered or ancient carbon dioxide back into the atmosphere or into the soil as ash. So I want you to think back to when we were talking about photosynthesis and cellular respiration. That is modern carbon, meaning it was recently in the atmosphere, it just cycled and it returned to the atmosphere. Combustion is releasing old carbon. The carbon in fossil fuels has been out of circulation. It has been sequestered for millions of years. It has not been cycling through the atmosphere for a long time. So when we begin to burn it through combustion, we're adding that carbon, that ancient carbon, back in to the cycle, which ups the overall amount of carbon that is cycling through the atmosphere. And there's consequences to that. Okay, so humans screw up the carbon cycle. Again, no surprise, not a surprise. And we screw up the carbon cycle a lot. There's been a lot of talk about carbon dioxide, greenhouse gas, global warming, and it's just obviously big political talk. Well, let's get down to the science of it. Before the Industrial Revolution, concentrations of atmospheric carbon had changed very little in the last 10,000 years. And while it is true that concentrations of atmospheric carbon have fluctuated over Earth's history, we have a pretty good idea of how they fluctuated based on ice core data. The Industrial Revolution began the wholesale combustion of fossil fuels, which added large amounts of this long sequestered carbon, this ancient carbon, back into the atmosphere very rapidly. Carbon dioxide is a greenhouse gas, and you guys have heard this term before. And this excess atmospheric carbon dioxide traps heat and warms the earth. Global warming is creating climate change. That's not an opinion, that's what science tells us. Deforestation alters the carbon cycle as well by reducing the amount of atmospheric carbon that is actually sequestered or taken out by plants. So we talked about how deforestation screws up the hydrologic cycle. It also screws up the carbon cycle. If you think back to photosynthesis and cellular respiration, during photosynthesis, some of that carbon dioxide is sequestered by the plant for use in its own tissues. And so if you get rid of the forest, then the plant is not holding on to that carbon. If deforestation also includes the burning of the plant material that you just cut down, then the combustion of that plant material adds additional carbon dioxide to the atmosphere. So not only are you cutting down the forest and removing the source of carbon sequestration, but you're also burning the plant and taking all of its sequestered carbon and basically putting it back up to the atmosphere. And here is a lovely picture of the carbon cycle. We will be doing some work with the carbon and the nitrogen cycles in class. And so this is just kind of a way to jog your mind a little bit. The pink arrows are what's going up into the atmosphere. The blue arrows are what's coming down. So kind of let's follow a few of these here. We've got the burning of fossil fuels, releasing carbon dioxide into the atmosphere, plant respiration, obviously, and of course, human and animal respiration. They both release carbon dioxide. And deforestation. And you can see that in this particular one, the forest is on fire as well. So we're not only removing the trees through deforestation, which reduces sequestration, but we're also combusting those trees, which puts additional carbon dioxide into the air. Here's the part that I was talking about exchange. And yes, there's oceanic photosynthesis and respiration, because y'all know that the photic zone, the upper layer of the ocean is photosynthetic. There's a lot of photosynthetic algae and phytoplankton that's doing its little photosynthesis in that top layer in the photic zone. But that's not the only way that we're having gas exchange, that we're having carbon exchange there. Remember, we also have the dissolving of atmospheric carbon dioxide into the top layer to create carbonic acid and calcium carbonate. So this is the exchange part that we were talking about earlier. This one tends to get kids a little confused here. So it's oceanic exchange in that top level. And it's a continual process, and it happens relatively quickly. So let's talk about these blue arrows on this side. What kind of processes remove atmospheric carbon dioxide? Well, we talked about them. There's photosynthesis right there. So plants uptake carbon dioxide during photosynthesis. And the storage in land plants is referring to the carbon sequestration that I just talked about. the carbon enters the soil via organic matter. So how does carbon get back down into the soil? Well, it can get down into the soil obviously through plant death, or through animal death or animal excretion. Plants don't poop, so plants don't excrete, but they do die. And when they die, their carbon is returned to the soil. Animals die, but they also poop. And in those two ways, the carbon is returned to the soil, okay? So we've got this soil carbon right here, eventually undergoing sedimentation and burial to create fossil carbon. And let's address this arrow here. In a marine environment, all the stuff that dies in a marine environment is also undergoing sedimentation and burial to become fossil carbon. And that's a crustal resource. So there it is down in the crust. And over the course of millions of years, we end up with fossil fuels from that fossilized carbon. And that's where we are right here. Then we have our extraction, and we have our burning, and the entire cycle begins again. Okay, let's talk about the nitrogen cycle. So nitrogen is a limiting agent for producers. I've used the term limiting agent in multiple other presentations. I'm going to tell you what it is one more time. Plants need nitrogen, a certain amount of nitrogen, in order to grow and thrive. So a limiting agent means it's something that limits the growth and survival of producers. Earth's atmosphere contains 78% nitrogen, but it's gaseous nitrogen. It's diatomic, N2, and it's biologically unavailable to producers. Producers cannot use gaseous nitrogen in their bodies. So the nitrogen must be fixed, meaning it must be converted into bioavailable forms before it can be used by producers. So that process is called nitrogen fixation, and it can occur two ways. It can occur biotically or abiotically. So biotic nitrogen fixation is performed by bacteria. Some of that bacteria lives in the root nodules of leguminous plants. That bacteria is called Rhizobium azotobacter. A leguminous plant is like a pea or a bean plant, and they have these weird roots that look like they have growths on them. The growths are what is called root nodules, and inside those root nodules is this Rhizobium azotobacter bacteria. It grabs the atmospheric nitrogen and it converts it into nitrates that the plant can use. Now, nitrogen fixation can also be done by free-living soil bacteria. When I use the term free-living in the nitrogen cycle presentation, I mean it's not attached to a root nodule. So fixation can be done by free-living soil bacteria, and that process converts atmospheric nitrogen into ammonium and an ammonium ion, NH4. And there's additional processes that have to happen to that ammonium ion for it to be bioavailable to plants. Root nodule fixation directly creates nitrates, and the plants love it, and they can directly uptake that form of nitrogen once it's been fixed. Abiotic nitrogen fixation occurs primarily through lightning strikes. I know, that's weird. When lightning strikes the earth, it's actually fixing nitrogen wherever it hits the ground. So it's it's converting diatomic nitrogen into nitrate. And actually, this is actually a very important way that nitrogen is fixed. So another step in the nitrogen cycle, and again, don't panic because we're going to go through all of this in class, and we're also going to go through it, briefly here in the presentation on a picture. Ammonification is the transformation of fixed nitrogen compounds by free-living soil bacteria into ammonium, and we talked briefly about that on the last slide. So there's soil bacteria that takes these fixed nitrogen compounds and creates ammonium out of them. The nitrogen can come directly from the atmosphere, or it can be released by decomposers during the breakdown of dead organic material. So ammonification is the creation of ammonium. So once we have an ammonium cannot be used directly by plants. So we've got to do something else to it so that the plants can get what they need. They need to get nitrate ions. And so how do we do that? Well, we take that ammonium and we nitrify it. It happens in two steps. It's the transformation of ammonium first into nitrites, which is NO2, by free-living soil bacteria called Nitrosomonas. Then the second stage of that is the transformation of those nitrites, those NO2s, into nitrates, NO3, by a different free-living soil bacteria called Nitrobacter. So again, 2 steps to nitrification. We're taking the ammonium that was produced during ammonification, we're turning it first into a nitrite, which plants don't really like to use. So again, it's still not bioavailable. And a free-living soil bacteria does that, Nitrosomonas. And then we're transforming it again from a nitrite to a nitrate by a different free-living soil bacteria, and that's Nitrobacter that does that. Assimilation. Assimilation is when producers uptake those now bioavailable nitrates. There it is right there. Oops, my pen's not working. All right, so at the end of nitrification, we have nitrates. Nitrates are what plants want. That's the form of nitrogen that they prefer to uptake. So assimilation is the name of the process when those producers are taking those nitrates up into their tissues from the soil. So what do they use that for? They use the nitrogen to make DNA and to make proteins. If you think about the structure of DNA, there's nitrogen in it. And if you think about the structure of proteins, one of the things that makes a protein is the fact that it has nitrogen in it. All right, so because the nitrogen cycle is a cycle, the bioavailable nitrogen, the nitrates, have to somehow be converted back into atmospheric nitrogen so that we don't deplete atmospheric nitrogen. So this is actually done through a process called denitrification. It's performed by anaerobic bacteria that do not use oxygen. And these bacteria live in swampy, waterlogged soil or in sediments at the bottoms of bodies of water. These tend to be areas that smell kind of funny. Part of that is what's called the biological processes that are going on there. There's decay going on, but there's also denitrification going on there. So these anaerobic bacteria take the soil nitrates and they break them back down into their inorganic component, and that atmospheric nitrogen is returned back up to the atmosphere, and the whole thing starts again. Yeah, I know the next part's again going to be a huge surprise. Humans screw up the nitrogen cycle, and we screwed up quite a lot. And we do it mainly through fertilizers. So fertilizers that are applied to your grass domestically or to agricultural crops contain nitrogen because nitrogen's a limiting agent. So if we want more crops to grow, we add more nitrogen. So, but this excess fertilizer can run off into local waterways, and we get what's called eutrophication. When we talk about water pollution, we're going to talk more about eutrophication, but what this is the overgrowth of aquatic plants due to excess nutrients in the water. Algal blooms are the result of eutrophication. Algal blooms reduce water quality because the excess growth of that algae and some of the aquatic plants. Now, let me be clear. Algae is not a plant. It's a protist. But it's a photosynthetic organism. That algae grows and grows and grows and grows. It uses nitrogen as well. And it overgrows, basically. It's not supposed to be growing like that. Well, eventually, all that biomass dies. And the increased decomposition by aerobic bacteria reduces the amount of dissolved oxygen in the water, because if you have more decomposition, you have more aerobic bacteria. That aerobic bacteria is using up all the oxygen in the water. Well, if the bacteria are using up all the oxygen, then everything else that lives in the water doesn't have any oxygen, like the fish and everything else. So the water becomes what we call hypoxic. Hypoxic means low oxygen, and it becomes a dead zone where nothing else can live. So we end up with these fish kills. You'll see whole big areas where all the fish have died, and it's because the water doesn't have enough oxygen in it due to eutrophication. Heavy fertilization also leads to the reduction, this should say in, not is, in terrestrial species diversity, because plants that thrive naturally under low nitrogen conditions can't survive when we artificially fertilize soils. So what we do when we add fertilizers to soils is we skew our species diversity, our species competition, diversity and composition, sorry, lost my word there, the composition towards those plants that thrive in high nitrogen soils rather than in low nitrogen soils. So all those ones that normally survive with low nitrogen conditions, they can't make it when you put fertilizer down. And I struggle with the nitrogen cycle diagrams that I didn't create myself, but part of it's because they don't always include all the parts. This is the best of the bunch, but there's still some parts missing here. And we're gonna go through this one in class, so I'm not gonna piece by piece this all out, but I'm gonna kind of walk you through. So we're gonna start up here with the atmospheric nitrogen. Atmospheric nitrogen, we're gonna follow this arrow around right here, can be fixed by nitrogen fixing bacteria living in legume root nodules, and that's what's going on right here. This is bacteria. Now notice here that arrow goes right back into the plant, because when that nitrogen is fixed by the plant, those bacteria are directly creating nitrates and is bioavailable to the plant, and the plant just uses it, takes it up and assimilates it. This atmospheric nitrogen can also be fixed this way by free-living soil bacteria, and that's this down here. And that free-living soil bacteria, through the process of ammonification, creates ammonium ions. So here's our biotic ways of fixing atmospheric nitrogen. Leguminous roots or free-living soil bacteria. If we go this route through the free-living soil bacteria, we end up with an ammonium ion. Well, ammonium ions are terrific, but they're not bioavailable to plants. So we have to do some other stuff here. Oh, by the way, here's the other thing. This arrow also leads to ammonium ions. So plants die, animals die. Plants die, animals die. They also poop, animals poop. And the decomposers grab the dead plants and animals and the animal poop, and they break it down and they create ammonium from that as well. So here's our arrows that lead into decomposers, and our decomposers lead down into ammonium. So now we're right here in the process. So the ammonium ion has to go through 2 steps of nitrification, and that's what we talked about before. Here's our first step. And that's our step that uses nitrosomonas. So this is a nitrosomonas bacteria. Nitrosomonas creates nitrites in the soil. Wonderful, but nitrites are still not bioavailable to plants. So we have to go through another step, and this is Nitrobacter. Nitrobacter creates nitrates. And this, my friends, is what plants want. This is plants' preferred way that they uptake nitrogen. Now, some plants can actually uptake nitrites, but that's not as happy. The plants aren't as happy. So there's our assimilation arrow, because now we're at the kind of nitrogen that the plants want. And then the plants, of course, do their planty things with the nitrogen. But that nitrate has to eventually be reconverted back into atmospheric nitrogen. And that happens by this denitrifying bacteria that occurs in swampy soils. Yay. Okay, phosphorus cycle. You've probably never heard of this. If you don't take APES, most people never hear about it in high school, but not you, because you're in APES and you're going to hear about the phosphorus cycle. Phosphorus cycles between terrestrial and aquatic systems. Test question alert. There is no gaseous phase to the phosphorus cycle. It's the only biogeochemical cycle that does not have a gaseous phase. Frequently asked in roundabout ways on the APES exam. So the phosphorus can cycle 2 ways. It can cycle biotically or abiotically. So if phosphorus is cycling biotically, this is how we're going to do it. Like producers, nitrogen, of course, has to go through 80 million steps before producers can use it, but not phosphorus. Unlike nitrogen, producers can directly uptake inorganic phosphorus and assimilate it into their tissues. Phosphorus is primarily used to make nucleic acids in producers. The phosphorus is returned to the soil when the dead bodies of plants and animals are broken down by decomposers. That's the biotic cycling of the phosphorus cycle. It's relatively straightforward. The abiotic cycling happens during like weathering and erosion. So phosphorus forms these stable and insoluble compounds in water. Once phosphorus gets into water, it's very non-reactive. It forms these stable, insoluble compounds, and it tends to precipitate out in water. If you remember chemistry, that means that a solid is produced in a liquid, and then it settles down to the bottom of these aquatic systems, creates sediment. The sediment is buried, and eventually that sediment turns into phosphorus-containing rock. The phosphorus-containing rock is eventually geologically uplifted through crustal movements, and then the weathering of this phosphorus-containing rock erodes the rock, which returns phosphorus to the soil, and then we go from that phosphorus in the soil back up here into the plants. The plants assimilate the phosphorus, and then the phosphorus is returned, and we do the whole thing again. Phosphorus cycle is pretty straightforward. But like everything else in this class, humans screw up the phosphorus cycle. And we largely do it in the same way we screw up the nitrogen cycle. So phosphorus, like nitrogen, is a plant growth limiting agent. Plants need it to grow. It's found in minimal amounts because the phosphorus cycle is a pretty slow process. So if you give plants more phosphorus, they grow bigger. Unfortunately, we tend to give them too much, and so we cause problems. So commercial fertilizers contain phosphorus in addition to nitrogen. And just like nitrogen, excess phosphorus containing fertilizer runs off into bodies of water. It creates eutrophication and algal blooms with all the same negative impacts on water quality that excess nitrogen produces. Just a note on phosphates. Phosphates used to be added to detergents, specifically laundry detergents, to help them make suds and clean better. But the phosphate-rich water that was discharged from household washing machines was causing huge algal blooms in the mid part of the century and into the 70s. So detergent manufacturers stopped adding phosphates to laundry detergent in 1994. In fact, if you, like we were cleaning out my grandmother's house to move her into a different house, and she had like old laundry detergent and, from like the early 1990s, and it was real big, phosphate free. It was a big, huge selling feature that, they were phasing out phosphates in the early 90s. So the laundry detergent that you buy today is phosphate free. It is, there's all kinds of legislation about that. So you're not putting that water back, that phosphate rich water back into the water system. However, there is not legislation that bans phosphates in like hand dishwashing liquid. So your hand dishwashing liquid may still contain phosphates. 16 states actually ban phosphates in dishwashing liquid. And I'll just say that most manufacturers have voluntarily made their dishwashing liquid, their hand dishwashing liquid, phosphate free by choice. Because what they've found is that it's a selling point for consumers. So they can put the label phosphate free on their product. And consumers actually tend to choose those over products that contain phosphates. So even though there's not legislation that says that they have to do that, it's a marketing point. And here's the phosphorus cycle. Again, I'm not going to go into this very much. You just need to know that, again, we've got, and I don't really do much with the phosphate extraction from mines, but the reason that phosphate extraction is there is because through geologic uplift, we have the rocks, the phosphate-containing rocks that are at the surface. So we've got erosion from those phosphate rocks. We can also have phosphate extraction. The erosion runs off into streams and rivers. Of course, it's also uptaken by plants. There it is right there. And it's returned when plants and animals die. Some of those phosphate compounds can also run off and get into water systems. We've got dissolved phosphates. Again, they tend to create pretty stable compounds. Those things go down into the marine sediments or the water sediments. They're buried, and they create additional phosphate-rich rock, which goes back over here. There's also, of course, some phosphate uptake by algae and other photosynthetic organisms because the phosphate compounds can be directly uptaken by those, just like they can on land. Notice that there's nothing in the atmosphere in the phosphorus cycle because there, again, is no gaseous phase. Sulfur cycle. This is the last of our cycles. So without human intervention, most sulfur exists naturally in rocks and is returned to the soil via uplift and weathering. Producers uptake sulfur as sulfate ions, which is SO4 2 negative, to form proteins. So sulfate ions is how plants prefer to grab their sulfur. And of course, they're creating proteins with those. The gaseous component of the sulfur cycle occurs naturally via volcanic eruptions, which spew out things called sulfate aerosols. But again, humans come along and they screw up the sulfur cycle. So how do we do it? The burning of fossil fuels is the main way that we do it. The burning of fossil fuels, particularly coal, releases huge amounts of sulfur dioxide. The sulfur dioxide combines with water vapor in the air, and it creates sulfuric acid, H2SO4. Sulfuric acid is a major cause of acidic precipitation and soil leaching. So obviously we don't want acid rain, and we don't want all the minerals leached out of our soil. So acid rain's bad, as is soil leaching. We are adding additional sulfur dioxide to the atmosphere, which messes up the sulfur cycle. Here's a picture of the sulfur cycle. Here's atmospheric sulfur up here. I don't know, when I start these cycles, I usually start up in the atmosphere. It makes me happier to start up there. I don't know why. So how do we get atmospheric sulfur up in the atmosphere? Well, volcanic eruptions are a natural way, or what we call a non-anthropogenic way of doing that. Human emissions, hydrogen sulfide or SO2, and I'm gonna add that actually, sulfur dioxide. Hydrogen sulfide or sulfur dioxide, those are human emissions, and they of course go back up into the atmosphere as well and add sulfur to the atmosphere. So when we're talking about the sulfur cycle, the emissions, right, can be natural or they can be anthropogenic. The word anthropogenic means man-created. So we've got precipitation and fallout into terrestrial ecosystems. This fallout is a nice way of saying acidic precipitation. And I'm just going to write precip there. And of course, when it hits the ground, it does all kinds of different stuff there. We're going to talk about acidic precipitation in a different presentation, so I'm not going to really go into that, but it damages ecosystems and causes the leaching of minerals out of the soil. The sulfur, of course, goes back into the soil. We've got decomposition of the hydrogen sulfide. It can also be buried. It can form organic compounds there. It can be uptaken by plants as sulfate ions. It can undergo runoff and end up in marine or freshwater ecosystems. And of course, marine producers also use sulfate ions just like terrestrial producers do. You don't need to know about this pyrite stuff. That's a mineral sedimentation and burial thing. Okay, that's the end of biogeochemical cycles. Yay.